Today, we're going to take a different direction for a little while. We're going to talk about recursion. It is a powerful and wonderful tool for solving computational problems. We're then going to look at another type of compound data structure, a dictionary, which is also mutable. And then we're going to put the two pieces together and show how together they actually give you a lot of power for solving some really neat problems very effectively. But I want to start with recursion. Perhaps one of the most mysterious, at least according to programmers, concepts in computer science, one that leads to lots of really bad computer science jokes. Actually, all computer science jokes are bad, but these are particularly bad. So let's start with the obvious question. What is recursion? If you go to the ultimate source of knowledge, Wikipedia, you get something that says, in essence, recursion is the process of repeating items in a self-similar way. Well, boy, that's really helpful, right? But we're going to see that idea because recursion, as we're going to see in a second, is the idea of taking a problem and reducing it to a smaller version of the same problem and using that idea to actually tackle a bunch of really interesting problems. But recursion gets used a lot of places. So it's this idea of using or repeating the idea multiple times. So, wouldn't it be great if your 3D printer printed 3D printers? And you could just keep doing that all the way along. Or one that's a little more common, it's actually got a wonderful name, it's called mise en abîme in art, sometimes referred to as the Drost effect. Pictures that have inside them a picture of the picture, which has inside them a picture of the picture, and you get the idea. And of course, one of the things you want to think about in recursion is not to have it go on infinitely. And yes, there are even light bulb jokes about recursion. If you can't read it, it says, how many twists does it take to screw in a light bulb? And it says, if it's already screwed in, the answer is 0. Otherwise, twist it once, ask me again, add 1 to my answer. And that's actually a nice description of recursion. So let's look at it more seriously. What is recursion? I want to describe it both abstractly or algorithmically and semantically, or if you like, in terms of programming. Abstractly, this is a great instance of something often called divide and conquer, or sometimes called decrease and conquer. And the idea of recursion is I want to take a problem I'm trying to solve and say, how could I reduce it to a simpler version of the same problem, plus some things I know how to do. And then that simpler version, I'm going to reduce it again and keep doing that until I get down to a simple case that I can solve directly. That is how we're going to think about designing solutions to problems. So semantically, this is typically going to lead to the case where a program, a definition, a function, will refer to itself in its body. It will call itself inside its body. Now, if you remember your high school geometry teacher, she probably would wrap your knuckles, which you're not allowed to do, because in things like geometry, you can't define something in terms of itself, right? That's not allowed. In recursion, this is okay. Our definition of a procedure can, in its body, call itself, so long as I have what I call a base case, a way of stopping that unwinding of the problems when I get to something I can solve directly. And so what we're going to do is avoid infinite recursion by ensuring that we have at least one or more base cases that are easy to solve. And then the basic idea is I just want to solve the same problem on some simpler input with the idea of using that solution to solve the larger problem. Okay, let's look at an example. And to set the stage, I'm going to go back to something you've been doing, iterative algorithms. For loops, while loops. They naturally lead to what we would call iterative algorithms. And these algorithms can be described as being captured by a set of state variables, meaning one or more variables that tell us exactly the state of the computation. It's a lot of words. Let's look at an example. I know it's trivial, but bear with me. Suppose I want to do integer multiplication, multiply two integers together, and all I have available to me is addition. So a times b is the same as adding a to itself b times. If I'm thinking about this iteratively, I could capture this computation with two state variables. One would just call the iteration number, and it would be something, for example, that starts at b, and each time through the loop reduces by 1, and it will keep doing that until I've counted down b times, and I get down to 0. And at the same time, I would have some value of the computation. I might call it result, which starts at 0, first time through adds in a, next time through adds in day, and it just keeps track of how many things have I added up until I get done. And yeah, I know you could just do mult, but this is trying to get this idea of how would I do this iteratively. I might start off saying there are b things still to add, and result is 1. The first time through the loop, I add in a, reduce I by 1. Next time through the loop, I add in another a, reduce I by 1, and you get the idea. I just walk down it until eventually I got to the end of this computation. So we could write code for this, and actually it should be pretty straightforward. There it is. I'm going to call it mult_iter. Takes in two arguments, a and b, and I'm going to capture exactly that process. So notice what I do. I set up result internally as just a little variable I'm going to use to accumulate things. And then there's the iteration. As long as b is greater than 0, what do? Add a to result, store it away, reduce b by 1, and I'll keep doing that until b gets down to being equal to 0, in which case I just return the result. Simple solution. Now, let's think about this a different way. Again, a times b is just adding a to itself b times. And that's the same as a adding a to itself b minus 1 times. Okay, that sounds like legerdemain. That sounds like just playing with words. But it's really important, because what is this? That's just a times b minus 1 by the definition at the top point. And I know you're totally impressed, but this is actually really cool. Because what have I done? I've taken one problem, this one up here, and I've reduced it to a simpler version of the same problem, plus some things I know how to do. And how would I solve this? Same trick. That's a times b minus 2. I would just unwrap it one more time. And I would just keep doing that until I get down to something I can solve directly. A base case. And that's easy. When b is equal to 1, the answer is just a. Or I could do when b is equal to 0, the answer is just 0. And there's code to capture that. Different form, wonderful compact description. What does it say? It says, I'm at the base case. If b is equal to 1, the answer is just a. Otherwise, I'm going to solve the same problem with a smaller version and add it to a and return that result. And that's a nice, crisp characterization of a problem. A recursive definition that reduces a problem to a simpler version of the same problem. Let's look at another example. Classic problem in recursion is to compute factorial, right? N factorial, or n bang if you like. N exclamation point is n times n minus 1 all the way down to 1. So it's the product of all the integers from 1 up to n, assuming n is a positive integer. So we could ask the same question. If I wanted to solve this recursively, what would the base case be? Well, when n is equal to 1, it's just 1. In the recursive case, well, n times n minus 1 all the way down to 1, that's the same as n times n minus 1 factorial. So I can easily write out the base case, and I've got a nice recursive solution to this problem. If you're like me and this is the first time you see it, it feels like I've taken your head and twisted it about 180 degrees. I'm going to take it another 180 degrees, because you might be saying, well, wait a minute, how do you know what really stops? How do you know what really terminates the computation? So let's look at it. There's my definition for fact, short for factorial. Right? Fact of n is if n is equal to 1, return 1, otherwise return n times fact of n minus 1. And let's use the tools that Anna talked about in terms of an environment at a scope and think about what happens here. So when I read that in or I evaluate that in Python, it creates a definition that binds the name fact to some code, just all of that stuff over here, plus the name for the formal parameter. Hasn't done anything with it yet. And then I'm going to evaluate print of fact of 4. Print needs a value, so it has to get the value of fact of 4. And we know what that does. It looks up fact. There it is. It's